And we're back. Problem 21-27. Almost to the end here. We have a 15-pound disc that is rotating about this axle with some initial angular velocity, and we have a given applied moment, and that moment in the problem is given by 4e to the 0.1 t pound feet. And we want to know what is our value of the angular velocity, omega 2, when our time is equal to 2 seconds. Now, what makes this one tricky is that, of course, we have this tilted disk. We know the moments of inertia of a thin disk. Those are ones we can look up inside the back cover. However, it's not listed what the moments are when we're rotating it like this. However, earlier in the section, they discussed how to determine the moment of inertia about an arbitrary axis, so that is what we're going to do. We're going to first imagine tilting our frame such that we have a new axis, which I'll call z prime, perpendicular to this disk. We'll have this direction that I'll call x prime, and now in this tilted frame, we do know what the moments are. So looking back in the book, for example, the moment of inertia about this z prime axis, called it IZZ, is equal to 1/2 of mr squared. And the other two moments, I x prime, and I y prime, will be equal to 1/4 mr squared. Because the disk itself is symmetric, all of our products of inertia, all of those cross terms, is equal to 0. So that will simplify things later when we go and compute the new moment about this axis. The mr squared, we're told that this is 15 pounds, but remember that that's the weight. So our value of mr squared is going to be 15 pounds divided by g, 32.2, multiplied by our value of the radius, 0.8. That gives us 0.298 slug feet squared. Always like talking about the slug feet. The other thing that is happening is that we have this time variable moment, and that is going to provide an angular impulse to our problem. And in fact, one of the simpler things we can do in here is integrate this exponential moment, which really do sound like the lyrics to a Phil Collins song. Gonna exponentiate this moment from 0 to 2 seconds. This is what the quarantine is doing to me. Anyway, so integrate from 0 to 2. We have an exponential function that gives us 8.856 pound feet seconds. So we have this moment in our tilted frame. Of course, then we need to go back and find it in our original frame, which is along this axis AB. And so if we look at how this is rotating, the axis, this direction, which we'll call U hat AB, is going to be tilted at a 45-degree angle relative to our new axes. So in our tilted frame, this vector U hat AB, we can write as, it's going to have a negative x prime component, so negative cosine 45. It's going to have nothing along this y direction, but then a positive z prime component, so this is going to be sine 45. Again, this is a vector that is represented in this tilted frame. In the end, we only care about the value of the moment of inertia along this particular axis. Now, there was an equation back in the section 21.1, and that was equation 21-5, that showed us how to find the moment of inertia about an arbitrary axis, and it was this big, long, nasty equation. We had 6 different terms, and things were squared, and it's not something that's easily rememberable, but if you looked at what I wrote, the extended discourse about the moment of inertia on the webpage, we can also write this in a more compacted tensor form, where we have this U hat AB transpose dotted into our moment of inertia tensor dotted into our U hat AB, and that corresponds to this row vector, negative cosine 45, 0 sine 45, multiplied by this 3 by 3 matrix of 1/4 omega mr squared 1/4 mr squared 1/2 mr squared. That's all along the main diagonal, and then because my products of inertia are 0, I have zeros everywhere else, and then finally I have my column vector, negative cosine 45, 0 sine 45. So this, at least personally, I find much easier to remember. This 3/3 times a 3/1 gives a 3/1, then times a 1/3 ends up giving one single number. Multiplying all this out, this gives us 0.112 slug feet squared. So that is the moment of inertia about just this axis AB. So via conservation of angular momentum, we have our initial moment, or rather we have our moment, which is 0.112 multiplied by our initial angular velocity, which was 8 radians per second, plus this integration of an exponential moment, yeah, plus 8.856, thank you for backup vocals, my wife there, multiplied by 0.112 times omega 2. Then putting all that together, this gives us omega 2 is equal to 87.2 radians per second. That wasn't so bad.